Hello and welcome, class. Today we are going to be continuing in our discussion of Chapter 4, which is all about taking our electrons, building our atoms, looking at how these atoms behave. We are, in this section, going to be focusing on what the effective nuclear charge is, so we're going to introduce this term, and then discuss what it means and how it relates to periodic trends. So as a reminder, last time we talked about group trends specifically, so those types of periodic properties that we can witness and categorize and discuss all in terms of the columns on the periodic table. Today we're going to be introducing the trends as they move from left to right as well, and how then we use effective nuclear charge to make sense of them. Alright, so we are going to introduce what the periodic properties are in terms of kind of generic definition, but we're going to define it again relative to group trends. So these are the types of trends that we talked about in Part 2 lecture. Again, these are the ones that we can observe and categorize, characterize based off of the columns that we're witnessing on the periodic table. The group trends we tend to observe are those that pertain to the reactivity of certain elements, and one of the examples that we walked through last lecture as well, as a reminder, was the reactivity of lithium versus potassium as they get submerged or interact with water. Now we saw just a picture of both lithium and potassium interacting with water, where lithium kind of like fizzed around the surface, kind of skated around in the picture. It doesn't really react too vigorously, whereas potassium set on fire. There was this very nice, right, lavender kind of blue, or lavender purplish kind of flame. Now the reactivity of both lithium and potassium as they get added into water can be attributed to the fact that they both have one valence electron. In addition, potassium's more extreme reactivity can be said to be due to the higher orbital shell, the fact that it is a 4s electron compared to lithium's, which is only a 2s. Okay, so the periodic trends are those that pertain to the horizontal rows on the periodic table. And that's not to say that these two types of trends are mutually exclusive. In fact, periodic trends tend to function both observably, or they vary observably horizontally on the periodic table and vertically, but we haven't talked about any of the vertical or horizontal trends yet. So the horizontal trends are due to what is known as the effective nuclear charge. Now the effective nuclear charge has to do with how many protons a given electron in an atom sees. So if we're looking from the perspective of a valence electron inside of some type of atom, let's say sodium's, where there's only one valence electron and it is in the third shell, a 3s electron, versus chlorine, where we can see they have the exact same core, they both have a neon core. Sodium only has one electron outside of that core, chlorine has 7 electrons outside of the core. So the difference in the periodic trend can be said to be due to the difference of the numbers of electrons on the outside compared to how many protons on the inside each of these electrons is going to sense. Now, it's not just going to be a one-to-one correlation. We actually have a way to kind of estimate how many protons each of these electrons are going to see, and how then this varies horizontally across the row is going to dictate the types of reactivities, the types of trends that we're going to be talking about, such as size and metallic character, just to name a couple. All right, so what we're going to do, the order of conversation, is we're first going to look at effective nuclear charge in greater detail, and then we are going to use it to describe, again, these periodic trends as we go horizontally across a row and vertically along these columns. Okay, so effective nuclear charge goes by a couple of different variables, but the one that we are going to use is capital Z for the atomic number, and a subscript of EFF standing for effective. So this is effectively how many protons or how many atomic units each of the electrons is going to see. which that is what the definition is that we have listed directly underneath. This is the actual magnitude of positive charge that a given electron is going to experience in the atom. Now, the reason why there is some variability, why each electron does not see every single proton inside of the nucleus, is because the inner electrons shield the outer electrons from the nucleus. So we can get an illustration for that, a sense for what this means if we look at the diagram on the right, and then we're going to turn to our equation on the left. So our diagram on the right, if we are hanging out, let's say, in this outer orbit with our valence electron, this is the 3s1 electron in the element of sodium. Well, sodium, if we observe the periodic table, we'd see has an atomic number, which is equal to the number of protons that the element has. It has an atomic number of 11. So there are 11 protons crammed inside of this nucleus. If we, though, are standing out here in the third orbit with this valence electron, there are a total of 10 other electrons that are potentially in between it and the nucleus. Now, a really good example for, or an analogy for this type of situation is, let's say you're at a concert and you are on the fringe, right? You are in the back of the concert. We can think of you as being that valence electron. So if the stage is up here and you are all the way back here, well, you're not going to be the only person at this concert, right? You're not going to be in full view of the band that's on the stage, or the band we can think of as being the protons in this case. And there's you as the valence electron. No, there's going to be a whole crowd of people in between, right? And all depending on how vigorous this crowd is, how much they're like moshing or jostling around or dancing around or moving around, you're going to get a view of the band up in the front, but the people that are in between are going to be getting in your way, right? Especially if some of them are taller, some of them are really close by, they're going to be bumping into you. You, as this valence electron, are not going to be able to see this band 100% of the time. So this is what we call shielding. All of these other people are all of the other protons and all of the other like rings or orbits or orbitals that get in your way. They're blocking your view. So if you are hanging out with this 3s1 electron, we can calculate what the effective nuclear charge of this electron is, and it turns out that the value is 2.2. So of all 11 protons that are going to be standing on this stage, you as this valence electron are only going to, on average, ever see 2.2 protons at any one given instant in time. The other electrons are just whizzing right on by, they're constantly getting in the way. Okay, well, how do we calculate this 2.2 value? How can we determine what the effective nuclear charge of any given electron is in or for an element? Well, for that, we can now turn to our equation on the left. The effective nuclear charge is a pretty simple comparison between the number of protons an atom has and what the shielding factor is. So in order to figure out what the effective nuclear charge, our Zeft value is, we first must look at the periodic table. And this is going to tell us how many protons for whatever element it is that we're working with. The shielding factor, we're going to have to take a little bit of a deeper look at it in order to figure out how to calculate this shielding factor here. In order to determine our shielding factor S, we are going to have to follow what are known as SLATER'S shielding rules. Now, if we observe these 5 rules, we are going to be able to determine what the shielding factor is going to be as it pertains to either some valence S or P electron. Now, there are more complicated rules for the D electrons, for the F electrons, but here in this general chemistry class, we're just going to keep it simple. We're just going to look at the S's and the P's. These are the main groups that we observe in general chemistry on the periodic table anyway, so we're just going to keep it simple. All right, so the first step of our rule is we are going to have to write out the electron configuration for our element. And then we're going to have to pick out the electron that is of interest to us, and it's more than likely going to be a valence electron. All right, the outer electrons, and this is just a formality situation, Electrons that are on the outside of where we are concerning ourselves with do not shield our view. They don't block our view. So the reason why this is a formality is, again, oftentimes we are going to be concerned with the valence electrons, but we can technically calculate the shielding factor and the effective nuclear charge for any electron inside of the atom. So even if we're working with, just to go back a slide, clean this up a little bit, we could calculate what the effective nuclear charge is for this electron. We could calculate what it is for this electron. Any electrons in the atom that are behind the element or the electron that we are interested in don't count. And so this is kind of the equivalent of, if we go back to that stage analogy, if you, let's say, push your way through the crowd, you're now a little bit closer to the stage. There are going to be people at the concert who are going to be behind you. These people, though, do not block your view of the center stage, right? If people are behind you, you can still see the stage just fine. So this is what rule number 2 means. If electrons are in higher shells, if they are behind you, you don't have to worry about them. They're not going to contribute to your shielding factor at all. All right, so rule number 3. So we are here. Adjacent electrons in the same shell are going to shield you 35% of the time. So these are going to be the people at that concert. I'm just going to keep using this analogy. It seems to be working pretty well for the or for describing what it is I'm trying to say. So let's say you are here. This is you, and there are some other people standing right next to you. Well, if these people are really starting to get into the music, if they're starting to dance a little bit, if they're starting to bump back and forth, they're going to like kind of push you around. You're going to end up moving along with like the mosh or the dancing or the jumping in the crowd. This is still going to disturb your view of the stage in some way though, because instead of getting a really nice straight view, you're now going to be getting kind of a wibbly view as you are also moving around. So the electrons that are right next to you are going to be bumping into you, blocking your view, or at least disturbing your view 35% of the time. And we are going to walk through an example to see how each of these rules kind of translate mathematically, but for now we're just kind of laying out what they mean. Okay, rule number 4. Electrons in the n-1 shell are going to shield you 85% of the time. So these are people that even though they might be in the next row up from you, they're going to be a little bit further away and they might be out of your field of vision. So these people are going to, again, assuming that they're kind of also moving around, they might get in front of you occasionally, most of the time, but they're not going to block you 100% of the time. They're only going to block you 85% of the time. Now, the electrons that are in the innermost shells, the shells that are equal to the n-2 or deeper, and we are assuming here that n represents where you are. So let's say hypothetically if we are that 3s or that third s electron, our n is going to equal 3, and so n-1 would be 3 minus 1 equals 2, and n-2 would be 3 minus 2 is equal to 1. So we're kind of looking layer by layer closer and closer to the nucleus. Right, so this is a hypothetical. This is an example situation. It's not always going to be 3. If we are in the 4s orbital, then our n is going to equal 4. If our valence electron of interest is in the 5s orbital, it's the n is going to be equal to 5, etc. All right, so if though, returning to rule number 5, if the inner electrons are in n-2 or deeper, we are always going to see them. They are going to shield us 100% of the time. So the people that are closest to the stage, the people that are closest to the nucleus, are almost always in our field of vision, and if they're like jumping up and down, they're going to be getting into our way, they're going to be blocking our view. So they are always going to negate our view of the nucleus a little bit. Okay, now that we have these rules at least written down on paper, let's walk through an example. So what we're going to do is find the shielding factor experienced by a valence electron in chlorine. So we're not going to walk through the example of sodium, instead we're going to walk through the example of chlorine. And the usefulness here is that in walking through this example, we're going to be able to compare our shielding factor for sodium versus chlorine and compare our effective nuclear charge for sodium versus chlorine. This is going to give us a good idea for how effective nuclear charges result in differences between our atoms as we move across the periodic table horizontally. All right, so let's start with our shielding factor for the valence electron in chlorine. So I'm just gonna go back and forth between our rules in this example so we can continue to see like where we are. So rule number 1, we have to write out the electron configuration, and we're gonna pick out the electron of interest to us. All right, so the electron configuration for chlorine, we can use the periodic table as a roadmap or a guide. In order to get to chlorine, we're gonna have to pass through our 1s2, or our 1s subshell, 2 electrons in it. We're gonna have to go through the 2s subshell, put 2 electrons in that. 2p, 6 electrons go there. 3s2, so 3s orbital, 2 electrons go there. And then finally we make it to the 3p subshell and 5 electrons are present here. So there is 1 electron missing, keeping it from becoming completely full. Only 5 electrons present in that 3p subshell. All right, so what does it mean to pick out, though, your electron of interest? Well, we are looking at a valence electron in chlorine, and most notably, we are going to be looking at the subshell that was the most recently filled. Since chlorine is a p block atom, meaning that it's an element that's found in the p block of the periodic table, we are going to be the most concerned with that outermost, not only valence shell, but also subshell. We're going to be paying attention to the 3p orbital and its 5 electrons. Now, if we want to calculate the shielding just for a valence electron, we're going to pick out one of these electrons to be the electron that we want to pay the most attention to. So what we're going to do is rewrite this 3p5 in another way. It's going to help us kind of pick out, again, when it comes to calculating our shielding factor, again, which electrons do we want to pay attention to, which electrons contribute to that capital S. So I'm just going to rewrite our electron configuration. Everything on the inside stays the same, 1s2, 2s2, 2p6, 3s2, and here's where the difference is going to be. We're going to pick out one of these 5 electrons. The other 4 electrons are the ones that are going to be adjacent to us. So this is us. We are here. The 3p electrons, the other 3p electrons, are those that are adjacent to us in the subshell. So we are one of them. The other 4 we're just setting aside, and they are going to contribute to the shielding factor S. All right, so rule number 1, check. We have written out our electron configuration, and we have picked out the electron of interest to us. This is one of our 3p valence electrons. Now, outer electrons shield us 0% of the time. Since there are no electrons behind us, since we are in the most valence shell and subshell, there are no electrons behind us in outer shells. So we don't really have to pay attention to this rule. We can just skip right on over it. It doesn't apply to us. All right, rule number 3 is going to be where we start calculating some stuff. So adjacent electrons in the same shell are going to shield us 35% of the time. Now the shell that we are in, our shell, is n equal to 3. Our shell is n equal to 3, which means all adjacent electrons are going to be those that have the n value in its quantum number set also being equal to 3. So rule number 3 is going to tell us then that we need to pick out all of these electrons that are adjacent to us. Not only these 3p electrons that are immediately adjacent, but also the 3s electrons, because they also have a quantum number of 3 in front of the s. So we can see that there is a total of 2 plus 4 electrons that are adjacent to us in the third shell. So there are 6 electrons total and they block our view 35% of the time. So what we're gonna do is multiply this 6 by 0.35, which is the equivalent of 35% just in decimal form. All right, we're gonna put a pin in this. We are going to add up everything in kind of one fell swoop as we go. So we're gonna add this to the results from our next rule. So this is check. Inner electrons that are in the n-1 shell are going to shield us 85% of the time. Well, if our current n is equal to 3, this means that the first inner shell is going to be n equal to 2, right? This is n-1. So now we have to work our way deeper into the atom. We're looking at the inner electrons in the next shell, where we can see that there are a total of 2 plus 6 equals 8 electrons that are in the n-1 shell, and we're going to see these 85% of the time. All right, we have one shell left. Just to go back, those are all of the electrons in the n-1 shell. Last but not least, we have to look in the n-2 shell, or deeper if we happen to be working in like larger atoms. All right, n-2 corresponds to our last little grouping in here. These are the deep electrons, which are going to be an n-1 in our case. We can see that there are only 2 electrons here, and each one of these 2 electrons we are going to see 100% of the time. So our total shielding factor is going to be a sum of each of these 3 cases, where the 6 electrons that are adjacent to us, again, are blocking our view 35% of the time. The electrons in the first shell in are going to be blocking our view 80% or 85% of the time, and the innermost electrons we see all the time. So our total shielding factor, which is going to be a sum of each of these things, is going to be equal to 10.9. In other words, if we are hanging out in the 3p subshell, we are going to see 10.9 other electrons at all times. There may be a total of 17 electrons inside of this atom, but we only see 10.9 of them because everything's moving around. This, right, all of the electrons in this atom are dynamic, and so we're going to see 10.9 of them at any given point in time. All right, so now that we have our shielding factor, we can use this to calculate what the effective nuclear charge that is, or the effective nuclear charge that is experienced by this electron that we're hanging out next to. Our effective nuclear charge is going to be equal to the atomic number Z for the element of chlorine, which is equal to 17. And we're going to subtract out that shielding factor that we just calculated, a total of 10.9. This gives us a grand total of 6.1, and this is equal to the, again, number of protons that are seen by the valence electron that we're hanging out with. So we see a total of 10.9 electrons, and we see a total of 6.1 protons. All right, in fact, I'm just gonna box this off a little bit. All right, so let's draw some comparisons. We're gonna go back to this lovely slide here. We're gonna compare sodium versus chlorine. So sodium is on the far left-hand side of the periodic table. Chlorine is in the same row, but it is on the far right-hand side of the periodic table. Well, our sodium, we can see here, the work was done for us. We could actually go through and calculate the effective nuclear charge for sodium. This is what we would come up with. Our Zeft is equal to 2.2. We can also reverse engineer without having to do any complicated work to calculate what our shielding factor is. That's going to be equal to the difference between Z and ZF, Z sub F. The shielding factor for sodium is going to be equal to 8.8. Now chlorine, we just went through and calculated everything. Our shielding factor here was larger than that in sodium. There were more electrons to shield our view of the nucleus. However, because all of the electrons that really got added in, like the difference between chlorine our sodium and chlorine, where all of the electrons that were being placed in the same subshell across the same row, our effective nuclear charge in chlorine ends up being greater than that of sodium. Hi, this is Dr. Billman here in editing. I don't know why sometimes my brain just farts when I'm trying to really explain a certain trend, and I could just put this into the description of the video, but it's really important that we get this clear moving forward. The reason why our effective nuclear charge increases from sodium to chlorine, despite the fact that the shielding also increases from sodium to chlorine, is because as we move across the row of the periodic table, we add a complete proton each step of the way, but only at a fraction of an electron due to how our shielding factor gets calculated. So because we add a complete proton, but only a fraction of an electron as we move from left to right, our effective nuclear charge increases. All right, on with the video. Sorry for the interruption. The greater effective nuclear charge in chlorine versus sodium is exactly where we're going to be getting some of the periodic trends we're going to be talking about. For instance, just to kind of like look ahead, if we consider the periodic trend of atomic size, how big is your atom? We actually find that sodium is bigger, chlorine is smaller. It is a smaller atom. And we can rationalize this by observing exactly what we've just introduced, our effective nuclear charge. If there are more protons being experienced by a valence electron, those valence electrons are going to be pulled in more tightly to the nucleus, right? Each one of these little valence electrons can see more of the nucleus, and so they're going to be more attracted by them. This is going to contract the size of our atom, not collapsing the electrons into the nucleus. As we've talked about, that's impossible, but we can contract the orbitals a little bit closer to the nucleus. This is going to decrease our atomic size. Now, this ends up being a trend across the entire periodic table. Larger elements are on the left-hand side because they experience lower effective nuclear charges. Smaller elements end up on the right-hand side because they end up with larger effective nuclear charges. All right, so the first periodic trend that we're going to introduce is exactly that which I kind of gave a little bit of foresight to: atomic size. Before defining the periodic trend, as we kind of have already hinted at, we have to talk about how we actually measure atomic size. Well, the first way that we can measure atomic size is known as the metallic radius. Now, the metallic radius is going to be mathematically equal to half the distance between the nuclei of two adjacent identical metal atoms. So let's say we are looking at something like copper, Cu. Well, we can, using a method known as diffraction, shine light, specifically we shine X-rays onto sheets of metal, like we kind of have loosely illustrated here, and all depending on how the light bounces off of these atoms and comes back to our sensors, our eyes up on top, we can get a measure for how far apart these atoms are from one another. Now, if we take, as we defined over here, half the distance between the nuclei of these atoms, so for example, if our distance is 372 picometers, we cut that in half, we end up with what is known as the metallic radius of copper, which is equal to 186 picometers in this case. All right, so we use a, again, method known as diffraction, kind of bounce it off of these metal surfaces, see how far apart these atoms are equal, or how far apart, sorry, these atoms are from one another, based off of what like these angles are equal to, etc. And we can come up with these cool distances. So this method, however, only really works for things that can come in like flat sheets, or can exist as solids. How we find other types of radii, like for instance the covalent radii, we have to use some alternate methods. The method that we use is similar to diffraction, just a slightly different setup. So long as we can condense our solids down, we can get an idea for how large these molecules are. For instance, something like Cl2. We are going to keep with a similar definition for what it means to be a covalent radius. We are going to be looking at half the distance between two different adjacent nuclei again. However, we can see that there's going to be a little bit of a difference between how we define a metallic radius versus a covalent radius, because covalent radii are dependent on a covalent bond being present. And by definition, covalent bonds correspond to like two atoms kind of smooshing into each other like this. Right in this great Venn diagram, we see that there is some overlap between these two atoms. What this means is that our covalent radius, which is measured right here, is actually going to be artificially shorter than reality. Right, if the bond length that we can measure between two different chlorine atoms is equal to 198 picometers, this is a shorter distance than one would expect because we are getting overlap between our atoms here. So our estimate of the covalent distance of chlorine being equal to 99 picometers is artificially shorter than what the actual radius of a chlorine atom is. Now we have some other ideas for how large chlorine atoms are based off of how, let's say, how large it is in certain like ionic species or other types of covalently bound species. So anytime you see like in the textbook, or if you continue in science in some type of article, sizes that are presented for different atoms, pay attention to how they found the size. Is it a metallic radius? Is it a covalent radius? Is it something that we call a van der Waals radius, where the two atoms that are being measured are actually slightly further apart than expected? So this is going to artificially increase your expected atom size. It would be nice if we could just take a picture of an atom, hold up a ruler, and say, yeah, this is how big it is. Sadly, we cannot do that just because of how incredibly small these atoms are. So we need to study the context with which these different materials exist in and kind of put together all of these different pieces of information to get a better average for what the approximately actual size of these atoms are going to be equal to. Now, if we do observe a wide collection, like what's the van der Waals radius versus the metallic radius versus the covalent radius for something like, let's say, sodium, we can get a pretty good idea, on average, how large it is compared to other elements on the periodic table. And from what we've been able to find by observing all of these different sort of average approaches, is that your atomic radius increases as we move down the periodic table. So it increases with atomic orbital value n, and it decreases from left to right with your effective nuclear charge. So we can see in this diagram, as it's labeled down below, we have an increasing atomic radius from top down and an increasing radius from right to left. So everything here is consistent with how we're describing things. Is just the diagram is just using the word increasing in both cases. So if we compared something like sodium and chlorine, which we already have done, the effective nuclear charge of our sodium, our Zeft, was equal to 2.2. And the effective nuclear charge for our chlorine was equal to 6.1. Because of the larger effective nuclear charge, our atom is going to contract, right? It's going to be smaller. And this is true for all of the elements that are present here in the right-hand side of the periodic table. They all are going to have larger effective nuclear charges when compared to elements further to the left. Because of that, we are going to have an increasing atomic radius from right to left on the periodic table. And as we go from top down, we're going to be adding shells. So for every new shell that gets added to the atom, for instance, hydrogen versus lithium versus sodium versus potassium, that was a bad last circle, we can see pretty straightforwardly, like as we add a new layer, we are going to be increasing in atomic size. Now, if you're asked to compare which is going to give you the larger versus smaller radius, like is the effective nuclear charge going to matter more, or is your quantum number n going to matter more? Well, it kind of depends. So if I'm asking you to compare two different elements on the periodic table, let's say phosphorus versus selenium, so these two here. As we move down on the periodic table, we would expect selenium to have the larger atomic radius because it has an extra shell. However, as we move from left to right, we would expect selenium to have the smaller atomic radius because it has a greater effective nuclear charge. So at the general chemistry level, because the answer just depends on so many exterior factors, it's really a good idea to actually just look up what the sizes are if you are asked. But if you're asked to give if you are asked to give a prediction, it is totally fair game to say, I don't have enough information. Don't have enough information to make that judgment call. Selenium could be larger because we're moving down, or it could be smaller because we're moving to the right. We don't really know. We don't have enough information here. It's going to be much easier to tell whether or not your element is going to be larger or smaller, just as we follow along this general diagonal. The smallest elements are in the upper right-hand corner. The largest are in the lower left-hand corner. So that's going to be the easiest way to make predictions and to tell, is if you're actually holding something in control, if you're moving truly up and down, or just left to right, or along the sum of this diagonal here. It's going to be the easiest way to tell. Otherwise, again, just to reiterate, it's totally fine to say you may not have enough information. All right, the other periodic trend that we're going to introduce today is metallic character. So when we first introduced the periodic table, I said that metals were on the left and non-metals were on the right. And I said we would be talking about later what types of characteristics define metal versus non-metal. So this is that day. We are now defining those characteristics. So most notably, metals are known for having low ionization energies and low electron affinities. In other words, it is very easy for metals to lose electrons. This is what it means to have a low ionization energy. It does not take a lot of energy to make something that is a metal, or take something that is a metal and turn it into an ion. The more interactive characters that metals are known for can be seen down below, though these are more of the physical properties. That metals are highly conductive, both in terms of electrical conductivity and thermal conductivity. So the first, right, electrical conductivity, this is why we are told, even as children, to not take a fork and plug it into an electrical socket. It's because that metallic fork is going to conduct all of that electricity and move it straight into your body. So it's very highly electrically conductive. And thermally, it is also very conductive. You can take a metal pan, put it on a stovetop, and if that stovetop is hot, the pan is also going to get hot very quickly. Metals are also known for being very shiny, malleable, which means they can get pounded into flat sheets, and they are ductile, which means they can be drawn into wires. All right, the combination of these last three characteristics are what lead us to being able to use metals in beautiful art sculptures, like we can see the xenomorph on the right, where there is a great example of, let's say on the headpiece, where the metal that was used has been pounded into a relatively flat sheet. However, all of these veiny kind of characteristics and the springs that are loaded in the head, all of these are examples for where it's been drawn into thin wires. And of course, the entire thing is incredibly well polished and shiny. Something that is very unique to the metals is that they can be so shiny like this. So it's really easy to even just look at the xenomorph, and if I asked you, hey, what type of material is this made of? You would say, I'm not sure what kind, but it looks like it's made of metal. It is because metals are shiny, they are malleable, they are ductile, and for this reason, they are all very easily identifiable like this. All right, so if that's what it means to be a metal, what does it mean to be a non-metal? Well, it turns out that by definition, a non-metal or a non-metallic material has all of the opposite characteristics from those that we've just introduced. So non-metals have very high ionization energies. They do not like to lose electrons. In fact, non-metals are most notable for having very high electron affinities, meaning that they like to gain electrons. They want to take all of those electrons for themselves. This is in part because they have very high effective nuclear charges, right? There are very visible protons from the valence shell in species that are non-metallic on the right-hand side of the periodic table. For this reason, because there are so many visible protons in the nucleus, even from the outside, they're going to be able, or these elements are going to be able to pull on electrons even from the outside and just hold them tightly. Non-metals are also known for being very insulating materials. These are things that do not conduct electricity, do not conduct either electricity or thermal energy. So if you were to take something like a plastic fork and shove it into the outlet, it should not conduct electricity. Please, for the love of God, do not try that at home. Just take my word for that. Non-metallic things don't conduct electricity very well. They also do not conduct a lot of thermal energy very well. This is why we use things like oven mitts in order to pull like hot pans out from the inside of the oven. They can conduct thermal energy, they just don't do it very well. So they are going to keep your hand nice and safe as you pull out hot materials from the inside of the oven, especially if you pull it out and set it down on another like hot pad right away. That'll keep your hands nice and safe. Non-metals also cannot be drawn into thin wires. They can't be pounded into flat sheets. They are in fact very brittle and crumbly in their solid form. We can get a really good visual for this by looking at the picture on the right. These are sulfur deposits. And all of this white chalky looking stuff here is sulfur. So sulfur is very brittle, it's very crumbly. It looks sort of like egg yolk, and in fact it feels kind of like firm egg yolks. Obviously, if you were to take a hammer and pound this type of like substance and try and pound it into a flat sheet, it would just fall into a million pieces. Similarly, things that are like gemstones are also non-metallic in character. They're very brittle, they're very crumbly. Same thing if you were to take something, some kind of like gemstone, and try and like pound it with some type of hammer, you're just going to break it into a million little pieces as it would fall apart. All right, so this is what it means to be a non-metal. Now we can, again, explain metallic versus non-metallic character as we move up and down the periodic table in terms of our electron orbital n, and as we move from left to right in terms of our effective nuclear charge. And it turns out that if we introduce a diagram like the one we've seen before, this time for metallic character, it very easily we can see metallic character follows the exact same trend as size. So as we go from right to left, we are going to increase the metallic character of our element, and as we go from top down on the periodic table, we are also going to be increasing our metallic character. So from this, we can conclude that elements that have very large atomic numbers n are going to have very strong or like notable metallic character. So that would make francium the most metallic element on the periodic table. Most metallic. Just like how before we also saw it was the largest. So it stands to reason that large elements are going to have more metallic character compared to something like helium, which is again on the opposite side of the periodic table, following the trend diagonally back upwards. This is going to be the least metallic and it is going to be the smallest on the periodic table, if we're just following this periodic trend. So helium's almost always going to behave as a non-metal. It is going to be very small, versus francium is very metallic and it's very big. So those are going to be the two periodic trends that we're going to introduce today. The metallic characteristic and the size of your atom. And again, we can use our electron configuration, notably observing our quantum number n, what shell we're working with, alongside our effective nuclear charge to get an idea for how to explain these types of group and periodic trends. All right, so that brings us to an example slide, the last slide also of the day. So I'm going to ask you guys, using a periodic table and what we have talked about, please rank the following elements from smallest to largest. This is also the equivalent of asking you to rank them from the least metallic to the most metallic. And we can see the 5 elements here that I am asking you to rank. So I'll give you the chance to do that, and then we will come together and compare our work. All right, welcome back. So we're going to find each of these elements on the periodic table first, and then we're just going to put them in a row. So I'm going to go back to the periodic table that is the closest in terms of slide, which is right here. I'm just going to clean this up a little bit. So the elements that we were asked to rank are aluminum, phosphorus, francium, let's see, calcium, and fluorine. So even just by circling these elements, we can see that they follow along a pretty nice line. I mean, calcium's kind of off of the line, but it's still up and to the right from francium, and aluminum is up and to the right from our calcium. Phosphorus is immediately to the right, and fluorine is up and to the right from our phosphorus. So we can see here that everything is pretty straightforwardly arranged. As we go up and as we go to the right, we are decreasing in our size and we are decreasing the metallic character. So if we are asked to rank the elements from smallest to largest, we're going to start with the smallest, which on this list appears to be fluorine, since it is up here in the upper right-hand corner, and then we are going to trace our way backwards all the way down to francium. So ranking the elements from smallest to largest means that we're going to start with fluorine, since this is the smallest on the list and the most non-metallic. There we go. Next up was phosphorus. Aluminum was to the left of that. Calcium was to the left and down from that. And francium is going to be the largest and the most metallic on all of the, or of all of the elements that we have looked at here on the periodic table. All right, so that is how we pick out and observe these two periodic trends that we have introduced here today. Again, atomic size and metallic character. And we can have all of these types of discussions about the predictions, which is going to be small, large, metallic, not metallic, again, all around the quantum number n and what our effective nuclear charge Zeft is. But in the meantime, I'm going to leave you with some example problems to complete. So we have some pertaining to the periodic table. We can see that these problems are from back in chapter 2. These problems all pertain to the characteristics that we have already talked about, so reactivity, group trend kind of stuff. The developments on the periodic table, these problems from chapter 4, all pertain to the size and metallic character. So we're just observing those periodic trends and the explanations for them. All right, so if anyone has any questions, please do not hesitate to leave them in the comments below. Or if you are in my class particularly, don't hesitate to email me. If you have any homework, do your homework. And until next time, class is dismissed.